Welcome back. In this section, we're going to learn what happens when we combine random variables by adding or subtracting them. We'll see how the mean and the standard deviation change when multiple random variables are combined together. And then we'll apply these same ideas to normal distributions and use the z-table to learn how to work with combined normal random variables in real-world situations. Things that might involve totals, differences, and measurements. In our first example of combining random variables, we're going to look at some data where we're given the averages or the means of two different variables, and we're also given the standard deviations of two different variables. And the question is asking us to find the standard deviation of the difference between these two variables. So let's take a look at our first problem. And then I'm going to show you a more simplified example so that you can see a proof of why we're using the formula that we're using. So this first example is about two people that are racing. They're going to be racing a 100-meter dash against each other. And it says, let A be Andy and J is Jim. And that's the time that Andy completes the race, and J is the time that Jim completes the race. And then they give us the mean for Andy is 11 and a half seconds to complete the race with the standard deviation of 1 second. And then they do the same for Jim, 10 and a half seconds as his average, and he has a standard deviation of half of a second. And it wants us to calculate D, which is the difference in their times. And it says find the standard deviation of D. Okay, so you might be thinking at a first glance that we would just subtract the standard deviations, 1 minus 0.5, and that is not how we do this. And we're going to look at another more simple example to explain why that is. So let's say that we have x minus y is what we want to find instead. We're going to say x varies by about 5 units. So its variability is, it could be -5 all the way to +5. And we'll say the same thing for y. -5 varies to +5. If we wanted to know the difference and find the standard deviations and the difference between these, if we just did 5 minus 5, that would give us 0. And that's not necessarily true. There isn't necessarily 0 variability between x and y. The actual variability between x and y would be a total of 10 units, not 0 units. So x could be as low as -5, and y could be as high as +5. And so the difference between that would be 10. So this is not correct. The difference is 10. But let's look at how we actually calculate this. So to find the variance of x minus y, we're going to use the variances instead of standard deviation. So to find the variance of x minus y, this is the variance of x, and we're going to add the variance of y to that. So we add the variances. Then once we have the variance, we can take the square root of the variance to find the standard deviation. So just as a kind of a side note, just a quick review, variance is standard deviation squared. And so this is standard deviation. Okay. Also, if we wanted to add the variances, The same equation is true because both variables still add randomness to the result. So we still get the variance of x plus the variance of y. So both of these equations are the equations that we're going to use for this section on combining random variables. All right, so that's kind of a side note so that we can look at why we're using these equations and why we're not just subtracting the standard deviation, because we can't just subtract the standard deviation. All right, so let's go back to our problem now and let's see if we can solve this. So we want to find the variance of a minus j. Let me zoom in a little bit more. So we want to find that, and the variance is written like this. And so that's going to be the variance of a plus the variance of j. Okay. And if we write the variance of a is standard deviation squared of a. And I'm just going to write it actually like this, plus standard deviation squared of j. Okay. So now we know what the standard deviation of A is. It tells us that that's 1 second. So we're just going to write 1 and then square it. The standard deviation of J is 0.5. And then we're going to square that. So now we have 1 plus 0.5 squared is 0.25. Okay, and so now we have 1.25. Okay, now this is, again, this is for the variance of A minus J. So this would be, I'm just going to write the variance of D, because we're defining D as A minus J. So the variance of D is 1.25. We're going to square root both sides to get the standard deviation of D. And that's just square root of 1.25. And if we had to simplify this, we could just type in our calculator. But it looks like that's our final answer on the multiple choice there. All right. Let's look at one more of these. This next example, I think, is very interesting because it gives us a lot of table data, and then it shows us these different equations that we could do with the variance. And when I first saw this, I thought that it was just like example one. But when I looked a little more closely at this problem, I noticed one thing that we have to be sure of, and that is we have to check to see if all the variables are independent, meaning that the variables do not influence one another. So this says that Jerome is a dietitian. He tracks his caloric intake from different sources of nutrients. And here's a summary statistics table for all of his daily values. And we want to let T represent the total calories from fat, protein, and carbs that Jerome consumes on a random day. So we have this data for fat, protein, and carbohydrates. We were given the mean and the standard deviation for these. And at first glance, I thought, well, we'll just find the variance like before. We could just say the variance of fat plus protein plus carbs is equal to the standard deviation, or excuse me, the standard deviation squared of fat plus standard deviation squared of protein plus standard deviation squared of carbs. That's what I thought this was at first. I thought we could just say, well, standard deviation or the variance of T would be equal to all of this. When I first saw this problem, I just thought, okay, let's solve it the same way as the first one. And then when we plug those numbers in, I ended up with answer choice B. But that's not correct for this problem. That's not how we solve this one. And the reason is these variables, they they're not independent. We have to ask ourselves this question about what's really happening in the word problem. If Jerome eats more food overall, will all of these variables increase or will just one variable go up? So if he eats more food overall, all three of these calorie sources are going to increase. And so because these variables come from the same total intake, which is calories, they likely move together. So without independence specifically stated, we can't combine their variances. So nowhere in here does it say that these are independent. In our first example, it did. And so here it doesn't. So if it doesn't state independence, then it cannot be determined from the information, and we cannot use that formula. Okay, let's go to one more example. Back to Andy and Jim. This is the same problem with the same data about Andy and Jim. Exact same mean and standard deviation. It's still about the 100-meter dash. And it wants us to find the mean of D, and it's defining D as the difference between the times of Andy and Jim. This is a much more simple problem. In fact, we don't even need independence in terms of this problem, but that's okay. It tells us anyway. So to find the mean of D, this time all we have to do is subtract. So we just find the mean of A minus the mean of J. It's much, much easier of a problem. Let's just 11.5 minus 10.5. So the mean of D is just 1.0. Okay. All right. Let's go to another type of word problem where now we're going to look at um, variables on the normal distribution. And we're going to practice using the z table again to find our answer. So some of this is probably going to be a review from the last section or two sections ago, and that's okay, but we are going to talk about how to determine what ranges of values that we're trying to find in terms of probability. Okay, so this question says that some nations require their students to pass an exam before earning their degrees. A nation gives their students an exam whose scores are normally distributed with a mean of 41 points and a standard deviation of 9. So they tell us that part. They tell us the given information. The mean is 41 and the standard deviation is 9. We want to select two testers at random, sort of like X and Y in that example where X was 5 and Y was 5, or A and J. And we're going to define the random variable D as the difference between their scores. We can assume that their scores are independent. So it tells us there's independence, that we can use uh, the the formula if we need to that we discussed earlier. Well, let's start by defining what D is. We're going to say test person number 1, their person X, and test taker number 2 is Y. So if we want to know what D is, it's the difference in their scores. So that's just X minus Y. Okay. Now, now it's asking us to find the probability that their scores are within 10 points of each other. So the probability that The difference in their scores is less than 10. That's how we read this part here. And so it just means that their scores have to be 10 points or less away from each other. And the absolute value just represents that it's the difference. So let's rewrite this so it's not absolute value. So now we're going to rewrite this as the probability that the difference in their scores is between -10 and +10. So the difference in their scores is less than 10 in either direction is another way we can say that. Okay, now to find the probability of that, um, this is, let me see where it says this. We're going to use a normal distribution. It says they're normally distributed. And that's very helpful for us because now we can assume that we're looking at a normal distribution like this, and we can convert to z-scores, use the z-table, and then we can find the area under the curve. And this probably is going to sound like review to you. And if it does, that's a good thing. That's great. So we want to find the area under the curve because that's our probability. And we're just going to use the z-score. So let's convert this to a z-score next. So if we convert this to a z-score, we're going to write z is equal to x minus mu, x, our data point minus the average, divided by the standard deviation of d. Okay. Now, for this next part, we are not just going to use the standard deviation that it gives us of 9 points. To find the standard deviation of d, we're going to do what we did in part 1 of this video. We're going to use the variance. So we're going to say that the variance of d is equal to the standard deviation, or excuse me, the variance of x plus the variance of y. So the standard deviation of d is equal to, now the standard deviation of x and the standard deviation of y, it says standard deviation of 9 points. That means that it's the same for student x and the same for student y. So now this is going to be 9 squared for student x and 9 squared for student y. Because remember, we're squaring the standard deviations. That's the variance. So now this is 81 plus 81. And again, we're just finding the variance of d first. And now we're going to square root both sides to get the standard deviation of d, which is approximately, when we type that in our calculator, square root of 162 is approximately 12.73. Okay, so now we have the denominator for our z value. Okay, but we still need the mean of d, which I should have written earlier, but the mean of d is what we're trying to find there. So again, we're not going to use 41 for the mean. We want to find the mean of d. So for the next part of our problem, we're going to find the mean. And so the mean of d is equal to the mean of x minus the mean of y, because d is the difference in the of, and then we're talking about the means. So the difference of means is just the difference in the means of x and y. And that was in one of our examples from earlier also. So now we're just going to say if there's 41 was the mean for x, and 41 is the mean for y. And when we subtract those, we get 0. Okay, so now we have those two values. Now we've got to figure out what x is for our z-scores. Well, we want a z-score for a range of values. We want our z-score for a range of -10, and +10. So we're going to find two z-scores. So our first one, we're going to plug in -10 for x, -0 was our mean, over 12.73 was our standard deviation. So our first one is going to be -10 over 12.73. And it's approximately, I'm just going to put an equal sign, but it's approximately -0.79. That's for our first z-score. And now we're going to go to our second z-score. We're going to use +10 for our second z-score. 10 minus 0 over 12.73. And we just get +10 over 12.73. And so that's positive 0.79. Okay, so now we have our two z-scores for this. So now we want to make sense of these calculations on the normal distribution. So let me see if I can copy this here. I think maybe I just got to move this up here. Okay. So we want to figure out what's the area under the curve for the z-scores that are associated with -0.79. Zoom in a little bit more. And positive 0.79. So we want to find what's the area under the curve here. Okay. So we would use our z table to figure out what these are, but first let's do some quick review on this. So to find this black region, we are going to find, so we're going to write this like the probability that our z-score is between -0.79 and positive 0.79 is equal to, we're going to say 100%. Let me scoot this over. We're going to say it's equal to, it's going to be equal to the probability that z is less than 0.79, which would be all of this. And then we're going to subtract out all of this part. Oops, I tried to do that in red there. Let me try that again. We're going to subtract out this part. And so this should be reviewed from a couple lessons ago. So the probability that z is less than 0.79 minus the probability that z is less than -0.79. That's what we're going to find there. Okay. So again, the probability that z is less than 0.79, that would be all of this blue stuff here. And then we're going to minus out the probability that z is less than -0.79, which is all of the red. And when we subtract that out, we're just left with the black region in the center. And that's going to give us our overall probability of where z is between these two values. Because remember, when we look at z-scores, we're only given the probability that z is less than some value on the z table. Okay, so let's go to the z table. So we are looking for z is less than 0.79 and z is less than -0.79. So here's our z table. So we want 0.79. There's 0.7 and there's 0.79. And then we want -0.79. So there's -0.7 and there's the 9. Okay. So I'm going to rewrite those values now up here so that we can have them here. So for Z was less than 0.79, that Z value was 0.7852 on our Z table. And for Z is less than negative 0.79, that Z value is 0.2148. And again, those were from the Z table, just looking at the table there. Okay, and when we subtract all that out, we get an approximate answer of 0.5704. And the question was asking us, based on the normal distribution, what is the probability that these scores are within 10 points of each other, where D is between negative 10 and 10. So we find the Z score of that. We did that. And that's the same thing as the Z-score probability between negative 0.79 and positive 0.79. And so when we round to the nearest two decimal places, we get 0.57 for our final answer for this one. All right. So a lot of steps there. We're using some knowledge that we had from a couple lessons ago, as well as these new variance formulas and difference in means formulas. Okay, so here's our next example, and I think this next example is important to look at because it's a little bit more challenging to figure out what our intervals are for the probability and the Z table. So this next question is about a car manufacturer, and they're producing two different items. They're producing valves and seals. And a seal goes onto a valve to ensure that whether it's air or liquid goes through that valve and it doesn't leak. So that's essentially what this problem is about. And it tells us a summary of the stats of the diameters for these valves and seals in millimeters based on how they were produced in terms of their average and their standard deviation in millimeters for both the valves and the seals. Okay, so it tells us that we're looking at a normal distribution, approximately normal distribution. So that's a good thing. That means we can use our Z table again for this problem. But some important information to note in this problem. It says a seal properly fits a valve if the seal's diameter is larger than the valves. And then it also says, but the difference in their sizes can't be more than 2 millimeters. Okay, so the first part that says the seal's diameter is larger than the valve's diameter, that's just going to be S is greater than V. And the difference of this is S minus V. Okay. Now, when I first saw this problem, I thought, well, maybe what we're trying to find is it says find the probability that the seal fits the valve, and it says probability of proper fit. When I first saw this, I thought, okay, maybe we're just finding the probability of that the difference is less than 2. But we can't say that in this problem, because if we did, then we would be looking at a distribution between -2 and +2. And we would want to find the probability between those, but there's there's no negatives. We can't have a negative value. Um, we we just can't. It's impossible because the seal has to be greater than the valve, and we're defining the difference as the seal minus the valve. Um, so we can't have negative values in this problem. Okay, So this is not what we're finding for our probability in this case. So let's redefine this in terms of S and V. I think this is the toughest part of the problem because we've learned about how to solve this with the Z table already in the last example, but now I'm going to rewrite this S minus V. We're going to say that the difference has to be between 0 and 2, not negative 2 and 2, but 0 and 2. If there was a 0 difference, then uh, it would be a perfect fit between valve and seal. And then if there is a 2 millimeter difference, then it would be just 2. So we can also write this like that. Okay. So we're going to use our same equation for the z-scores and the variance, but let's start with finding the mean this time. So if we want to find the mean of D, that's the mean of the the mean of the seal minus the mean of the valve. And here the order does matter. The seal it has to be larger than the valve, so that number has to go first. The seal has to go first. So the seal, the average for the seal is 51, and the average for the valve is 50. And so the difference in their means is just 1.0. Okay, so now we want to find the standard deviation of D because we want to find the z-score is x minus the mean of D over the standard deviation of D. And we're going to find those two z-scores again. But let's find the standard deviation of D now. This hopefully is some really good review because we've done this a couple of times now. So uh, the variance of D is equal to the variance of V plus the variance of S. Remember, we're always adding the variance. So now this is going to be the standard deviation squared of V is 0.3 squared plus standard deviation squared of S is 0.4 squared. And this is 0.09 plus 0.16. Okay, and then we're going to simplify this further, and we get 0.25 for the variance of D. And then we just take the square root of both sides to get the standard deviation of D. We get 0.25, and that gives us exactly 0.5. Okay, so now we're going to find our two different z-scores. We want the z-score for our first value. Our first value is if the difference in the seal and the valve is 0. So when x equals 0, so 0 minus 1 over 0.5. And we just plug in these numbers in from what we have. So now this is negative 1 over 0.5. And this is going to give us negative 2 for our first z value. For our second z value is z is equal to, now our x value is going to be 2. So we're going to plug in 2 for x. And our mean of d is going to be the same, 1.0, 2 minus 1 over 0.5. And that's going to give us 1 over 0.5. And this is positive 2. So now we're looking for, let me just bring this up here so we can get a good visual again of what we're finding on our normal distribution. So now we want to find the probability that z is between negative 2 and 2. Okay, so we want to find what is the area under the curve here. All right, so in order to do that, Let me just get one more of these normal distributions up here so we can get another illustration of this. Okay, so in order to do that, what we're going to do is we're going to find the probability that z is less than 2, which would be all of this, would be all of that would be probability z is less than 2. And then we're going to subtract out the probability of z is less than negative 2. So we're going to subtract out this stuff there. Okay, so let's go to our z table and figure out what z is less than 2 is, what the value is for that, and what z of less than negative 2 is. So we're going to go back to our z table and just find 2.0 and negative 2.0. Okay, so here's 2.0, and here is negative 2.0. It's like 0.9772 for z is 2.0 and 0.0228 for when z is negative 2.0. Okay, so now we're just going to plug these numbers in, and this becomes 0.9772 minus 0.0228, and that is equal to 0.9544. Okay, and this is the probability that z is between negative 2 and 2, which is the same thing as, let's go back up here, make sure our constraints are the same, which is the same thing as d, the difference is between 0 and 2. So we can also write it like this, that the difference is between 0 and 2. And I believe our problem wants us to round it to the nearest hundredth. So make sure if you're typing it in, it's 0.95, I believe is what we would get when we round that to the nearest hundredth. Okay. So again, hopefully that was some good review on the Z tables, and also a good new lesson on how we're adding the variances in order to find the differences in standard deviation.